power n, you first add 1 to the exponent and then divide by that exponent, and then plus our unknown constant c when it's an indefinite interval. But remember, that power rule works for every exponent except for -1. Because if you tried to use that same rule on x to the -1, if you add 1 to the exponent, you get x to the 0, and then you'd have to divide by that new exponent 0, and of course when we divide by 0, that's undefined, so that doesn't work. So we need some way to integrate x to the -1, which is really the same as 1 over x. And remember, in the previous lesson, we looked at the derivative of natural log of x, or the derivative of natural log of the absolute value of x, was 1 over x. So if we reverse that formula, that shows us that integral of 1 over x would equal the natural log of absolute value of x plus our unknown constant c. And it could be either written as 1 over x or x to the -1. Either way, it's the same thing. It gives you the natural log of absolute value of x. Now notice here, when you integrate, you always need the absolute value signs. The reason why is thinking about the domain. The domain of 1 over x, or x to the -1, you can plug in any number except for 0, right? Because 0 would make it undefined. Positive and negatives are both fine. So we want to make sure when you integrate it, we can also plug in every number except 0. And without the absolute values, you'd only be able to plug in positive numbers. But with the absolute value signs, that will change all the negative numbers to positive, so now we can still plug in everything except for 0, just like the original function. So anytime you have x to the -1 or 1 over x, it integrates to be this. We don't use our power rule like we do for every other exponent of x. So let's look at some example problems. We'll start with some indefinite integrals. So we've got 3x squared minus 4x plus 5, all divided by x. So remember, there's no quotient rule for integration. So when you have a single denominator, a monomial like this, x, then one technique that can often be helpful is if you split up the fraction. So if we divide each of these by x, that would be the integral of 3x squared divided by x minus 4x divided by x plus 5 divided by x. And of course the whole thing, parentheses, is multiplied by dx. Now let's simplify each one of these before we integrate. So be careful with your notation here. The integral sign is still there because we haven't integrated yet. Well, 3x squared over x, one of the x's reduces there, so you're just left with 3x. Minus, here the x is completely reduced out, x divided by x1, all you're left with is -4. And here, you could write this as 5, x to the -1, and then all times dx. And now, since these are just added and subtracted, we can integrate each of these separately, find the antiderivative of each one separately. So when you integrate or find the antiderivative of 3x, here we can use the power rule for integration. So we have 3, the constant stays out in front, and this is like x to the first, so you add 1 to the exponent, you get x squared divided by that exponent of 2. Minus, when you integrate a constant, it just gets multiplied by the variable. In this case, dx tells us the variable is x, so that would be -4x when it's just a constant by itself. And now here's where our new formula comes into play. The 5 stays out in front, that's a constant. And if you try to use the power rule, you'll discover you get x to the 0 over 0. That doesn't make sense, it's undefined. So that's where we use our new formula. When you integrate x to the -1 or 1 over x, you get the natural log absolute value of x. And again, since this is an indefinite interval, there has to be some unknown constant plus c, because the derivative of any unknown constant is 0, so it could be anything. So that would be our the answer to that indefinite interval. Okay, let's take a look at the next one here. On this one, again, no quotient rule, but we can't use that same technique we used here because we have 2 terms on the denominator. It only works if there's a monomial on the denominator. So splitting up the fraction is not an option here. Instead, what we can do is, to make this a simpler interval, we can use U-Substitution. Now, typically what we said u equal to previously, up until this point, was some function inside. But because of our new formula here, another thing that setting u equal to will also be helpful will be the entire denominator. We'll see why in this one. So if we say u equal to 3x squared minus 2, then that would allow us to rewrite this as 4x over, now we set the whole denominator equal to u, like that. And of course, we need to get this all in terms of u, so we need to replace the dx with something involving du, and the way we do that is by taking the derivative of what we say u equal to, du dx, the derivative of 3x squared, is 6x, the root of negative 2 is 0. And then when you solve that for dx, multiply both sides by dx, and then divide by 6x, you get dx equals du over 6x. So we can take that and substitute it in for dx right there. So we get du over 6x. And now you can see that x is reduced out. X divided by x is just 1. That's what we want to happen. So it's all in terms of u. The 4 6 is a constant. We can pull that out. And that also reduces if you divide the denominator by 2 to be 2/3. And all we're left with then is 1 over u du. And that's really what you want to be left with when you set u equal to the entire denominator. You're trying to get it to look like this formula. So we've got 2/3. When you integrate 1 over u, that's our new formula. That's the same as 1 over x, it's just a different variable. It'll give you the natural log, absolute value of u, again, since it's an indefinite interval, plus our unknown constant c. But since we use U-substitution as an indefinite interval, we want our answer back in terms of the original variable x. So that isn't quite our final answer because we have to substitute back in this 3x squared minus 2 back in there for u. So we get 2/3 times the natural log, absolute value of 3x squared minus 2, and then plus our unknown constant c. All right, let's take a look at another one that's slightly more complicated. Similar idea. Again, 2 terms on the denominator, so there's no quotient rule, so we can't integrate it like that. We can't split up the fraction. So again, let's try to use U-substitution. On this one, again, there's no function inside except for the 2x, but if you set u equal to 2x, you could try that, but what's going to end up happening is you'll have 4 sine of u, cosine of u plus 3. And that's still going to be too complicated to integrate. So rather than setting u equal to 2x, we're going to try the entire denominator like we did on the previous problem. So if we say u equal to cosine of 2x plus 3, let's see how we can rewrite this. So when you rewrite it, it'll be the integral of 4 sine of 2x. Now we set the whole denominator equal to u, so over u, and again we have to replace dx. So the way you can kind of foreshadow what's going to happen on this and see if it's actually going to work is by thinking about the derivative of what you say u equal to. And is that going to help you cancel out all the x's or not? In this case, it's 2x, you can think of that in parentheses. You can derivative cosine of 2x plus 3. Well, cosine of 2x, the derivative cosine is negative sine. The 2x stays inside, but because there's a function inside, we also have to use the chain rule and multiply by the derivative of the function inside. The derivative of 2x is 2. And then, of course, the derivative of a constant 3 by itself is 0. So then if we solve this for dx, you get dx equals du over negative sine of 2x. Sorry, negative 2 sine of 2x. And we can take that and substitute that in for dx. We can see that sine of 2x is going to help us cancel off the sine of 2x on the numerator. So instead of dx, we have du over negative 2 sine of 2x. And so then the sine of 2x's reduce out, which is what we want, get it all in terms of u. Then we've got 4 divided by negative 2, which is negative 2, and that's a constant, so we can pull that outside the integral. And then all we're left with again is just 1 over u du, which again is what you want to happen. When you say u equal to the entire denominator, you want to be just left with 1 over u so that it will fit this formula. So the negative 2 constant stays out in front, and then again, when we integrate 1 over u, same as u to the negative 1, you get the natural log, absolute value of u plus c. However, it's not our final answer again because it's got u in there, and this is an indefinite, we want our answer back in terms of x. So again, what we do is we take what we say u equal to, which is cosine of 2x plus 3, and the last step is to substitute that in back in for u. So you get negative 2 times the natural log absolute value of cosine of 2x plus 3, and then plus our unknown constant c. So there we took a look at 3 indefinite integrals that involve using our new formula. Now let's take a look at another indefinite integral and then one definite integral. So on this one, again, you can see setting u equal to 3x might be an option because that's a function inside, but it's still not going to be simple enough because we'd have 2e to the u divided by e to the u minus 4, which is still going to be too complicated. So again, let's try setting u equal to the entire denominator, which is e to the 3x minus 4. And again, that'll allow us to rewrite this as 2e to the 3x over u, and then we just have to replace the dx by taking the derivative, u dx. Here we have to use the chain rule again because the 3x is the function inside. So derivative e to something, remember that stays the same from the previous lesson. Derivative e to 3x, e to 3x. But again, using the chain rule, we have to multiply by 3, the derivative of 3x. And then when you solve that for dx, you get dx equals du over 3e to the 3x. And that's what we can substitute in for dx right there. U over 3e to the 3x. And then you can see that e to the 3x is reduced out. And you can pull out the constant of 2/3. And again, notice all we're left with is integral 1 over u du. So we can leave the constant 2/3 on the outside. When you integrate 1 over u, that gives you, using our new formula, the natural log absolute value of u plus c. And then the last step again, get it back in terms of x. So substitute back in, e to the 3x minus 4, back in for u. So you get 2/3 times the natural log absolute value of e to the 3x minus 4, and then plus c. Now let's take a look at a definite integral. Again, the way you can tell the difference is it has a lower and upper limit on the integral, as opposed to an indefinite integral that does not have those. So again, we can see splitting up the fraction is not an option. There's 2 terms on the denominator. There's no real function inside here. There's no quotient rule for integration. So again, let's try setting u equal to the denominator. In this case, 2x cubed plus 8. But since this is a definite integral, remember one of the different steps is you have to convert the lower and upper limits by substituting those in for x one at a time. So if we substitute 1 for x, we get u equals 2 times 1 cubed plus 8. Well, 1 cubed is just 1 times 2 is 2 plus 8 gives you 10. So when x is 1, u is 10. So our new upper limit will become 10. And now let's do the same thing with 0. If we substitute 0 for x, we get u equals 2 times 0 cubed plus 8. Well, 0 cubed is 0, times 2 is 0, plus 8 gives you 8. So when x is 0, u is equal to 8. So don't forget to convert those on a definite integral, something you don't have to do on an indefinite integral. And now what we have left in our integral, we've got 3x squared in the numerator, divided by, we set the whole denominator equal to u. And again, now we have to replace the dx with something involving du. So if we take the derivative, du dx, we get 6x squared using the power 1, and the derivative of 8 is 0. So then solving it for dx would equal du over 6x squared. And again, we can take that and substitute in for dx right there. So we get du over 6x squared. Again, we can see that x squared is reduced out. That's what we want to happen. 3, 6, we can pull that out as a constant, but that reduces to 1/2. And then all we're left with in our integral, in this case from 8 to 10, is 1 over u du. And again, now it fits the formula that we've looked at today. So you integrate 1 over u, again, that gives you the natural log, the absolute value of u. Okay. But this time there's no plus c because it's not an indefinite interval. Remember, it's a definite interval. So remember the official notation is it's written like this, from 8 to 10. But it's sometimes handy to turn that notation into a bracket like that. So it separates the constant out front nicely. So you've got a 1/2 in front, then you substitute in the upper limit, you get the natural log of, well, the absolute value of 10 is just 10. If it was a negative number, it would change it to positive. That's already positive. And then minus, you plug in the lower limit, you get the natural log of 8. Notice here, one thing we didn't do on the definite interval that we did on the indefinite interval, we did not plug in back in for u in terms of x. And the reason why we did not do that is because we already converted these to be in terms of u. So if you plug that back in for x, then these would no longer match up. These are in terms of u. We want this to be in terms of u as well. So let's pretend, for instance, that this is our right answer. You could leave it like that. Well, let's pretend that this was the AP test and this was a multiple choice question and you did everything right, you got this, but none of the choices look like this. Well, what could they have done to write it differently? This goes back to our log properties. So let's see if you remember those. When you have two logarithms of the same base, in this case they're both natural log, which is base e, and they're subtracted, remember you can condense them using your log properties, your laws of logarithms, by dividing. In this case, since it's subtraction, the one that's positive goes on the numerator, so the natural log of 10, the one that's negative goes in the number. So the natural log of 10/8, and 10/8 reduces to 5/4. So it also could be written as 1/2 times the natural log of 5/4. Both correct, there's two different ways of writing the same answer. And remember, if this had been a plus instead of a minus, then when you condense it into a single log, then you would multiply what's inside of it. So then it would become the natural log of 10 times 8. So if it was a plus, it would have been the natural log of 80, would be another way to write it using your log properties. All right. Now let's review some other concepts we did earlier this year. Just to happen to involve our new formula here. So it says find the average value of the function on the given interval. So here's our a and b. So remember the formula, anytime you're trying to find the average value on some function on some interval, you always start with 1 over b minus a, which in this case is e squared minus 1, times the integral from a to b, in this case from 1 to e squared, of whatever you're trying to find the average of. In this case, it's this function, so it'd be 4 natural log of x over x, then times dx. So in order to integrate this, we need this in a simpler form, no quotient rule for integration. So you might think, common mistake is, well, we've been saying u equal to the denominator all the time. What if you said u equal to x? Well, let's just think about it. If u is the same as x, du dx is just going to be 1, so dx would equal to u. This is going to be u, this is going to be u. When you plug these in, these are not going to change. The whole integral is going to stay identical, except it's going to have u in it instead of x. So setting u equal to x is never, ever helpful, because if u is the same as x, it's not going to change our integral at all. Okay? So don't fall for that mistake, because that never helps. Okay? You might want to write u equals x. That's not going to work. That's not helpful. Okay, so what are our other options? There's not that many of them. There's not really a function inside. This one's a little bit trickier. So what can we say u equals to make this simpler? Well, since we don't know how to integrate natural log of x, you haven't learned that yet, then it would make sense to say u equal to it to get rid of it. And let's see how that's helpful here. Well, on the outside, we'll still have this 1 over e squared minus 1. But since we're saying u equal to the natural log of x, we have to convert our lower and upper limits. So let's go ahead and substitute those in one at a time. So if we substitute in e squared, get u equals the natural log of e squared. And here's where it's helpful to remember that natural log is the same as log base e. And when you're looking for what a log equals, we're trying to figure out what does this equal. Remember remember the question you ask yourself, logs are equal to exponents. So the base e for what exponent would give you what's inside the log, which is e squared. Well, I can see e to what exponent is e squared, that's going to be 2. So when x is e squared, u is equal to 2. So our upper limit now becomes 2. And let's do the same thing for the lower limit of 1. And if u equals the natural log of 1, which, remember, is the same. Natural log is a short way of writing log base e, in this case of 1. So if you want to figure out what does this equal, again, the question you ask yourself is e the base to what exponent is going to equal 1? Well, e to what exponent equal 1? Well, that would be 0, because the base that's not 0 raised to the 0 power is always equal to 1 when you have a 0 exponent. So this equals 0. So when x is 1, u is equal to 0. So 0 becomes our new lower limit. And now let's see what we have left inside of our interval. We have 4. We said natural log of x equal to u, and we have over x. And now we just have to replace the dx with something involving du. So even though we didn't know how to integrate natural log of x, we did in the previous lesson, remember, learn how to take the derivative. And that's what we need to do right here. The derivative of natural log of x is just 1 over x. And here, when you have the derivatives of fractions, it's probably easiest to cross multiply here. So you get dx times 1 is just dx equals x times du. So we can take that and substitute in for dx right there. So x times du, and then look at what's going to happen. The x's are going to reduce out, which is what we want to get it all in terms of du. You can pull the 4 out as a constant. There's already a 1 over e squared minus 1, so if you multiply that by 4, that's going to make it just 4 over e squared minus 1. Interval from 0 to 2, and all that's left is just u times du. So when you integrate u, that just gives you, just using the power rule, u squared over 2. That's a definite interval, so from 0 to 2. So 4 over e squared minus 1. Then substitute in the upper limit, 2, gives you 2 squared over 2, minus the lower limit, 0 squared over 2. I guess we also could have pulled out the 1/2 here first if you wanted to. But we get 4 over e squared minus 1. 2 squared is 4, divided by 2 is 2, 0 squared is 0, divided by 2 is 0. So you end up with 2 times 4 over e squared minus 1 will give you 8 over e squared minus 1 is your average value. It may look a little weird. Remember, e is just a constant, so this is close to 8 divided by about 2.7 squared minus 1 will be your average value. So anytime you see a natural log of x inside the interval, you're going to use U-substitution, set u equal to that natural log of x to get it out of the interval to make it easier to integrate. Let's take a look at one more. And this goes back to an earlier lesson this year. We've got f prime of x equals 5x, so we have the equation of the derivative. And we know f of the cube root of e is 4, so we have one point in the function. And we're looking for another point in the function, f of e. Well, remember, when you have one point in the function, you're looking for another point, and you have the derivative. That's an initial plus change problem. So the value we're looking for is f of e. The initial one we're given is f of the cube root of e plus the change, remember, it comes from the definite integral from wherever your initial is, becomes a lower limit, in this case cube root of e, to wherever you're looking for it. You want to know how much does it change from a cube root of e to e, and then your derivative of whatever this function is goes inside the integral. The change comes from the definite integral of the derivative, which in this case they give you is 5 over x. So let's work out what we have here. So f of the cube root of e, they tell you is 4. Plus, here to make this easier to figure, you can pull out the constant of 5. And then we just have an integral from the cube root of e to e of 1 over x dx. This one already fits our formula. Notice it doesn't require U-substitution at all. So you have 4 plus 5, and then when you integrate 1 over x, and that's our new formula, that gives you natural log absolute value of x. But again, it's a definite integral. So the official notation is from cube root of e to e. But again, to make it easier to see what's really inside there, if you're writing this hard to tell some 4 inside there or not, if you turn that into brackets, it makes it a little easier to see. So you have 4 plus 5, and then we substitute those in, you get natural log. Well, e is already positive, approximately 2.71. So that's going to become the natural log of e minus the natural log of cube root of e is also positive. So the absolute value doesn't affect it either. If you did plug in a negative number, the absolute value would just change it to a positive. So let's see if we can simplify this at all by figuring out what's the natural log of e and what's the natural log of the cube root of e. Well, the natural log of e, remember, that natural log again is the same as the log base e of e in this case. So to figure out what this equals, the question you ask yourself is e to what exponent gives you what's inside the log, which is e. In this case, you can see that would just be to the first power. So the natural log of e is just 1. So we have 4 plus 5. We just figured out the natural log of e is 1. Minus, let's figure out the natural log of the cube root of e in a similar fashion. So the natural log of the cube root of e equals the log base e, is what natural log is short for, of the cube root of e. So again, we want to figure out what does this equal. So this is saying e to what exponent equals what's inside the log of the cube root of e. Well, what exponent would be the same as the cube root of e? Well, if you think about switching this from radical form to exponential form, you see this would be e to the 1/3. So that exponent would be 1/3. So the natural log of the cube root of e is just 1/3. So we've almost got it now. So we have 4 plus 5 times, well, 1 is the same as 3/3. Minus 1/3 gives you 2/3. So then we have 4 plus 5 times 2/3 is 10/3. 4 is the same as 12/3. You can multiply the number by 3. Plus 10/3 gives you 22/3. So that is what f of e would equal, 22/3. And that concludes the notes for AP Calculus on the topic of integration involving the natural log.